Okay, so now we're going to talk about tangent vectors and differential maps on manifolds. Okay, and the basic idea, if you will, is that one aim is to basically generalize the notion of a directional derivative. So I want to generalize the notion of a directional derivative. Okay, so let's just say d of f, okay, at some point x, and then in a particular direction, say eta. Okay, and of course it's like just in the linear space setting, it's like what that is of course just some limit as tau goes to 0 of f evaluated at point x plus t times eta plus minus f evaluated at x, okay, divided by t. Okay, so I want to generalize this to a real valued function f, which is defined on a manifold. Okay. And of course, one of the problems, if you will, it's like with a manifold or working on a manifold, then is that there's no real notion of how we say we add. It's like a vector. It's like to a base point and still get another point on a manifold. Okay. So let me sort of try to focus on perhaps what's the most intuitive way of thinking about this. All right. So perhaps the best way of thinking about this is the following. So sort of an intuitive way to generalize this is to consider, is to replace this map, if you will, so t maps to x plus t eta, okay, with some sort of just a curve. It's like on a manifold. Let's see, gamma on M. Okay, so M is the manifold. Okay, and the basic idea, if you will, is that with the property that gamma at 0 is the base point x, and then gamma dot at 0 is eta. Okay, so if you think about it, what basically is happening is that you're really, it's like, how should I best describe this, right? So what happens is that this directional derivative in the vector space case, df of x at eta, right, can be viewed as the limit, well, let me just write it this way, is the partial derivative with respect to t of f evaluated on some curve, let's say tau of t, okay, where tau of t, okay, is x plus t eta. Okay, so that's what's happening in the linear case, and of course it's easy to convince yourself that tau at 0 is x and tau dot at 0 is just eta. Okay, so that's, so trying to now replace this very specific curve, which is just sort of obtained by sort of moving, it's like at constant velocity, it's like in a particular direction. Okay, you can replace that curve now with some arbitrary curve in the manifold, but with still the property that the initial point is the base point and the initial velocity is the vector which you're working with. Okay, so that's basically what's going to happen here is that we're going to, instead of working with a base point and a tangent vector, we're going to work with a curve which goes through that base point at time 0 and whose derivative at time 0 is that vector. Okay, so as we'll see later, this is again a nice way of thinking about tangent vectors more generally on manifolds. Is basically a curve. It's like which you identify a tangent vector. It's like at a manifold or at a point on a manifold with a curve which goes through that point at the initial time, and whose derivative agrees with that tangent vector. And of course, it's like there's more than one possible curve. It's like which satisfies that property. So we're going to identify all those curves. It's like which have those properties as being identified as an equivalence class. It's like to the tangent vectors. Okay, so that's basically looking forward. It's like to how it's like you can abstract the notion of a tangent vector and more generally tangent spaces. And it's like to the setting of manifolds. Okay, so so let me sort of try to state it perhaps in a way which is easier to understand. So in essence, what happens is that the way you generalize a directional derivative so that it makes sense on a manifold, okay, is as follows. So I'm going to do the following. So I'm going to say df of x, right, is again, it's like in some direction, right, is going to be the partial derivative of f along some curve gamma. We have the property that gamma at 0 is the base point x, and gamma dot at 0 is this tangent vector eta. Okay, so the first question one would have to ask is whether or not that actually, well, you have to evaluate it at t equals to 0. So the question is that well defined, right? Okay, because so I gave you data which is the base point and the tangent. It's like at that point, and then on the right hand side, it's like I've defined it in terms of some curve. All right, so as I've sort of said before, there's more than one possible curve which satisfies these constraints. So you have to ask yourself whether or not this right hand side, it's like which is expressed for a particular choice of curve which is consistent with the data, is independent of that choice. Okay, and the claim is that it is. All right, so the claim is that yes, this is independent of the choice of gamma. Okay, as long as again gamma satisfies these two conditions. Okay, and in fact, again, it's like the fact that it's independent of this choice, as long as you specified the value at 0 and its first derivative at 0, then it's like again leads to this sort of equivalence class notion of the tangent space. Okay, so so again, modulo this issue of whether or not the thing is well defined. It's like you can check that the right hand side then makes perfect sense, because gamma is a map from, say, time. It's like to a point in the manifold. F is a map from the manifold to the rails. So this composition, it's like F composed with gamma is a map from R to R, right? So you can take the usual derivative. So that derivative makes sense in the usual way. Okay, all right. So all right, so let me just defer. It's like this discussion. It's like of whether or not that right-hand side sort of is well defined for a second, and then talk a little bit about the idea of tangent vectors. Okay. Okay, so let's talk about tangent vectors. Okay, so let's say M be a manifold. Okay, and then you have a map. We have a smooth mapping. Gamma from the rails to the manifold, right? This is just some sort of curve, right? And that is just a map from T to gamma of T, right? Is a curve. Right, in M. Okay, then so the problem is that the notion of defining a derivative in the usual sort of limit of a finite difference approach, say gamma prime of T, right, as gamma prime of T is limit as let's say tau goes to 0 of gamma of T plus tau minus gamma of T over tau, right, requires a vector space structure on M, because you're taking the difference of 2 points in the manifold. So in order to take the difference, it's like you need to assume that there's some sort of vector space structure in M, and we don't have that. Okay. Right, but this fails on an abstract manifold. Okay. All right. So how do you deal with that? Okay. So okay. So let's say we have let f be a smooth real-valued function. On M. Right. So the composition, right, of f with gamma is a map from R to R, which is again smooth. Okay. Right, with a well-defined classical derivative. Okay. Okay. So, so how do you define this notion of a tangent vector then? Okay. So let's see what happens. Okay. So. So we're going to use this, it's like in order to make sense of this notion of a tangent vector more precisely. Okay, so so let x be a point on the manifold. So let x be an element of M. Okay, and let gamma be a curve which goes through x at t equals to 0. Right, so that means that gamma at 0 is equal to x. Okay, and then let's say we have this sort of math frac f of x Okay, M. Okay, so let this be the set of smooth real value functions defined on a neighborhood of X. Okay, then I can, with that, I can define a map from the sort of the derivative, it's like, of gamma at 0 to this set of smooth real value functions, right? I can define a mapping from gamma dot 0, right? Sorry, I can define a mapping gamma dot of 0, okay, from smooth real valued functions to the reals. Okay, so in essence, what I'm going to do is that I'm just going to formally define for you how this thing, which I'm going to claim is like a vector, okay, maps smooth functions, it's like to the reals. Okay, so gamma dot acting on f, right? So the way you should think of this is really that I'm looking at f, it's like I'm thinking of this really as literally the directional derivative of f in the direction gamma dot. Okay, and so far I haven't really told you what gamma dot is, but nevertheless, that's what it is. Okay, so this is equal to the derivative of f gamma t dt evaluated at t equals to 0. Okay, for all f's which are in this space of smooth real valued functions in some neighborhood of x. Okay, so I'm going to claim that this mapping is the tangent vector. So let's sort of call this a tangent vector. To the curve gamma at t equals to 0. Okay, so all right, and the point basically is that this tangent vector is it's a mapping. It's like again from it's like functions. It's like to the rails, and you can sort of check that it's really a linear map. Okay, and the reason is because again the usual notion of a derivative of a curve, it's like which involves this finite difference, doesn't make sense on a manifold. You can, in principle, of course, make sense of this if you had coordinate charts, right? And as I sort of alluded to before, it's like there is sort of a way of identifying curves. It's like by the fact that their first derivatives agree at a particular time, and then defining an equivalence class. So you can, of course, do that notion of equivalences. It's like between, it's like curves. It's like on a local coordinate chart, and you can then check that that notion of an equivalence class is independent of the choice of coordinates. And that's another way to approach it. It's like this idea of a tangent vector is through that notion of equivalence classes, where sort of the equality or the equivalence is sort of checked on coordinate charts, right? On any coordinate chart, and any other sort of coordinate chart on sort of a smooth atlas, it's like it's going to give you the same notion of equivalence. Okay, so it's well defined, but there's again this idea of thinking of the tangent vector then as a map from functions. It's like to the rails, and if you think about it, this is really sort of saying that you think of literally the tangent vector as being some notion of a directional derivative, right? I mean, it's like, so you're thinking of the map as being a derivative of some sort. Okay, or a derivation more precisely. Okay. And I think it's like perhaps another way to think about this is that if it so happens that you have a manifold which is embedded, it's like into some sort of vector space where there is this notion of, it's like sort of a linear space structure which allows you to take the difference of 2 points in that space, then this notion of the mapping agrees with the usual sort of more classical notion of a derivative. Okay, so let me now try to more formally define for you. It's like what a tangent vector is. Okay, so I'll give you the definition. A tangent vector. So a tangent vector, let's denote this by cos C sub x to a manifold M, right, at a point x, right, it's a mapping from this space of real valued functions which are sort of local about the point x to R to reals such that there exists a curve gamma on M, okay, with the property that gamma of 0 is x, satisfying the following, that cos C x of f, right, is equal to gamma dot 0 acting on f, and that is, well, I mean, we have to define what it is, right, and that is defined to be d of f gamma t, okay, dt evaluated at t equals 0. Okay, and this has to be true for all f. It's like in sort of all real valued functions. It's like defined in some neighborhood of x, right? This is true for all f in mathfrak f sub x of M. Okay, then such a curve gamma, right, is said to realize the tangent vector. Cos Cx. Okay, and the point, of course, is that that curve, as I said, alluded to before, is not unique, and you can have more than one curve. It's like which satisfies this condition, right? And in particular, you can ask, it's like when two curves, it's like will be able to satisfy this position, and the way you do this is that you can write. It's like once you have, it's like the curve, which is a map from. So, all right. So you can ask. So let's say the question is the following, right? If gamma and gamma tilde, right, both satisfy sort of this equation, right? How do you check that, right? Okay, and essentially it's like the way you do that is that, of course, gamma is a map from the rails to the manifold, right? And then there are two of them, gamma and gamma prime. and then there's a map from the manifold. It's like by some coordinate chart. It's like to say Rn. Okay. So basically, the composition of the coordinate chart of gamma and gamma tilde are now maps from R to Rn, right? So I can talk about the time derivative with respect to the time variable of these two things, right? So I can check. So let's see. I'm just going to put the time derivative at the top. Hopefully you understand what I mean, right? Minus, I guess the notation was to do the prime. It's like for the classical derivative, right? Composed with gamma tilde prime, right? So you want this thing to be basically 0, okay? Evaluated at t equals to 0, okay? So, so the bottom line is that you can check. It's like when two candidate curves, it's like will both satisfy. It's like this condition by just looking at their coordinate representation and then taking the usual classical derivatives and checking whether the classical first derivatives agree at time t equals to 0. And if they do, it's like then you can check that this thing is going to be well defined. Okay. Well, let me phrase that. That those two curves will give you the same, will correspond to the same tangent vector, if you will. Okay. So again, you know what I'm basically saying of this is that you think of gamma x as this abstract notion of a tangent vector, then you have this realization of it, okay, by an actual curve. And then there's this notion that you know, more than one of these curves can satisfy or can realize the same abstract tangent vector. And the way you check that they are going to realize the same abstract tangent vector is that you compute the derivative of that curve in some sort of local coordinate chart. And if they agree at time t equals to 0, then they really are going to be part of that same equivalence class. Okay, so this is a rather convoluted way of saying again that there's some sense in which with this abstract tangent vector, right, you're going to identify it with some sort of curve. And then more or less it's like that abstract tangent vector is specified by knowing something about the value of the curve at time 0 as well as its first derivative at time 0. Okay, and then we're going to identify all curves it's like which have those two properties it's like which are the same, and then think of the equivalence class of those curves it's like with those properties as being related it's like to this abstract tangent vector. Okay, all right. Okay, so and you know, it's like, and the fact that this notion, this characterization is exactly what happens is the statement, if you will, of the next proposition. Okay, so I'll state a proposition now, but I won't prove it. Okay, well maybe I will. So let's actually just go ahead and state the proposition that this calculation I have here, indeed it's like telling you when two curves it's like are both realizations of the same abstract tangent vector. Okay. So the proposition is as follows. Okay, so two curves, let's say gamma 1 and gamma 2, true x at t equals to 0 satisfy the condition that gamma dot of 0 is equal 0, right? If and only if, right, given a chart, say, right, with x being a point, it's like in the domain of definition of the chart, right? It holds that the derivative of the curve, oh well, let me say, the chart applied to the curve, right, evaluate t equals to 0, right, is equal to this thing here, right? That's basically what I had said before, right? That when you do this composition, it's like you have a map from R to Rn basically, and so you can check whether these two things agree. It's like using the classical notion of a derivative. Okay, let me just prove the only if part, and well, okay, so the only if part is straightforward. Right, since each component of the vector valued sort of coordinate chart is it's just a smooth function. It's like defined at the neighborhood of x, right? Okay, so that direction is straightforward. So the if part right, given any f in, again, this set of smooth real value functions, it's like defined in the neighborhood of x, right? So the if part follows from this. Given this, it's like we have that gamma 1 dot of f is defined to be df gamma 1 of t, dt, evaluate t equals to 0, right? So this is equal to df, so I'm going to essentially sort of slot in the coordinate chart and its inverse, all right? And so the composition obviously is the identity on the manifold, right? So this is a map from U to Rn, right? So this composition, right, is now a map from U to itself, but it's essentially the identity on U, okay? All right, and F is just defined on the neighborhood, so you know, it doesn't hurt to just have it on the intersection. It's like of U, it's like with the neighborhood on which F is defined, right? And so I can look at this composition where I compose this with sort of the chart and its inverse, the inverse of the chart composed of the chart, right? Okay. All right. So, okay, evaluated at t equals to 0. Okay. And that's equal to d of f composed with gamma inverse. Sorry, not, yeah, phi inverse, right? Phi gamma 2 t, okay, dt evaluated at t equals to 0. Okay, all right, and then we have this equality because that composition yep, okay, yep, so actually no, yeah, so we have that equality, and then this is of course nothing more than gamma dot 2 at 0 acting on f. Okay, all right. So again, the bottom line is that you can check when two curves gamma 1 and gamma 2, it's like can be both thought of representing the same abstract tangent vector by looking at its, you know, it's like notion of a classical derivative of the curve. It's like in some local coordinate chart. And as is the case, it's like this notion is independent of the choice of the coordinate chart. Okay, all right. So now it's like we have this, in some sense, this equivalence class notion of it's like relating an abstract tangent vector to a family of curves which go through that point x. It's like with the property that they are local representatives of the derivatives at time t equals to 0 agree with each other. Okay, so all right, then the tangent space to M of x, right, denoted by T sub x of M, right, is the set of all tangent vectors to M at x. Okay, and then this has a vector space structure. Okay, as follows. Right, so if you have, so if you're given, let's say, gamma 1 dot 0 and gamma 2 dot 0 in txm, right, and AB in the rails, right, then I can look at what the linear combination of these things are. So A gamma 1 dot at 0 plus B gamma 2 dot at 0 acting on F. So again, you think of these abstract vectors, the abstract tangent vectors, as maps from functions to rails, right? So I want to give you some real valued thing. So this is just given by A times gamma 1 dot 0 acting on F, right? So this acting on F gives me a rail times A, right? Is again rail plus B times gamma 2 dot 0 acting on F. And again, it's like that gives me a real number. Okay. Then, so then you have to show that you can realize it's like this formal linear combination of two abstract tangent vectors as again a curve, right? So want to show we can represent A gamma 1 dot 0 plus B gamma 2 dot 0 as a curve, and we do this on a coordinate chart. Okay, so if you have a coordinate chart, right, then this curve gamma t, which is associated with this formal linear combination, is just given by the inverse of the chart applied to, right, A times the chart applied to the curve plus B times the chart applied to the curve. Right, so but the point is that if you have two curves, it's like, which gives you, if you have a curve, it's like which gives you a point in a manifold, you can apply the chart to it, that gives you, it's like a point in Rn, right? So you now have 2 points in Rn, which I can take linear combinations of using this linear structure of Rn, and then once I have that, it's like I take the inverse, it's like coordinate chart to give me a map, a curve, it's like back on M, right? And that's basically the candidate thing. And you can check that this has the property you want it to have. Okay? So let me try to finish this up. Okay, so the property that the tangent space is a vector space is important actually very important because you know, again, a lot of our computations are set up, it's like to assume that you have a vector space structure, right? So essentially what's going to happen, it's like you'll see later on, is that sort of intuitively what you have is that if you have a point X, it's like on the manifold, and you have some sort of neighborhood around that, right? Then what we're going to do is we're going to construct an identification between that and some neighborhood of the tangent space. Okay, so we're going to identify it's like some neighborhood of the point, it's like on the manifold M, with some neighborhood it's like of the origin, it's like on the tangent space, it's like to M. Okay, and of course it's like the advantage of being able to make that identification is that, well, on the one hand, it's like this neighborhood is a nonlinear space. There's no notion of addition. It's like, well, linear space structure to work with. On the other hand, it's like this neighborhood of the origin on the tangent space. It's like 2M is a vector space, and then we can do all the usual sort of linear operations you might have. Okay, and so we want to make this kind of identification. And this identification is going to be what is called a retraction. Okay, so there's going to be what is called a retraction, which is going to be the basic sort of tool. It's like which, you know, it's like this entire course, it's like on optimization on manifolds is based upon. So we're going to use, it's like, or introduce, it's like various notions of retractions. Again, the idea is to identify some neighborhood of, you know, it's like points, it's like some neighborhood, it's like on M, it's like of X, it's like with some neighborhood of the origin on the tangent space 2X, sorry, the tangent space at X, it's like 2M. And, you know, by sort of using this, it's like to go back and forth, it's like you can leverage some sort of algorithm, it's like for optimization, which is which uses the linear space structure here, and then pull it back, it's like to the manifold. So this is a little bit akin, if you will, to what you see here, right, where you use the chart, right, to give you exactly the linear space structure you need. It's like to take combinations of curves and then you pull it back by the inverse of the chart. It's like to give you a curve on the manifold. Okay. Yep. And then you can check that the dimension of this tangent space is equal to the dimension of the manifold. Okay, so let me just sort of state that in words. It's like, and you can check this using local coordinates. Okay, so you can check that the dimension of xm is equal to the dimension of the manifold. Okay, so and this can be shown using local coordinates. Okay, but I won't go too much into that. Okay, so hopefully that gives you, again, some idea, it's like, of how you can think of tangent vectors abstractly. And again, at a very high level, it's like the basic idea is that you think of identifying, it's like tangent vectors to the manifold, it's like with some notion, some equivalence class of curves which go through that point. It's like, and there's a sense in which the derivative of that curve agrees with that tangent vector. Okay, and then any other curve, it's like which goes to the point in which has the same derivative, then is part of this equivalence class of curves. It's like which I identified with that abstract tangent vector. Okay, so let me just stop here for now. Thank you.